Hello everyone, today we'll be talking about hash tables, which are the underlying system when we talk about unordered maps and unordered sets. So the point of a hash table is that we want to have a key mapped out to a value using a hash function. And we want this to be done in constant time. Otherwise, we could do it with something else, like a vector. We could just run through the vector and find what we're looking for. Instead, what we use is a hash table, which can find things in constant time. So when we take a look at a hash table, usually we have keys, which are over here, keys. Move that down for you, keys, and we have buckets over here. The material or the object that we use to store our values in. And depending on what the hash function will tell it, or what is outputted by the hash function, the keys will be mapped out to each bucket as such. So depending on what the hash function outputs when the key is put into it, we get a different source of bucket. And if we want to find that, we just put the key in and it'll return the value that we want it to. Now there are two things that tell us how good a hash function is. Consistency. If two keys are equal, they must hash to the same thing. If they do not hash to the same thing, it will be hard to look up. It won't be in constant time. It makes this whole array of issues that we do not want to deal with. Also, we want it to be we want to have every hash function must be computed in constant time. Otherwise, it defeats the purpose of even using a hash table. We can just use a vector and just iterate through it to find it if it's not constant. Now suppose I had a function that looked like this for my hashing function. So suppose I wanted to find out where the string cat would return and go into which bucket. So what I would do is I would go here at the first letter in cat is C. So that means that we'll do C minus A, we do some math there, and we figure out that that value is 2. So this value would return out 2. So cat would return 2. Suppose we had dog. Well, D minus A is 3, so that maps out to the third bucket. Suppose we had cow, and we wanted to map that out. We figured that C minus A is 2, but wait a minute, I already had something at 2. This is called a collision, and it's very common with these types of functions. We try to avoid them with all the functions that we write, but sometimes it gets a little hard to deal with collision. So what we have to do is we have to figure out a way to map it anyway. And that's what collision resolution is, which we'll be learning soon. Now there are two different ways to deal with collisions, and one of them is called separate chaining. So each bucket, we map out a key to each bucket, right? So for each bucket, we have a linked list that continues to store values as seen here. So suppose I had something that matches to this bucket here. I can continue to store it, and when I need to look something up, I can continue to iterate down the linked list until I figured out what I wanted to see. But there are a lot of caveats to this. For example, if all of your keys map to the same bucket, then what occurs is that we will actually need O of n time to figure out where your value is for your key that you specified as the worst case. That seems to occur a lot with separate chaining. So what we do instead is that we have different type of open addressing, where we iterate to a different bucket to find out where it goes. Now going back to our old hashing function, we can see how we can use open addressing to figure this out. So suppose we're given 4 words, and these words are cat, cop, ear, and cart. So let's map all of these out. So this maps out to the value 2. This will map out to the value 2. This will map out to the value 4. And this will map out to the value 2. Suppose we have 5 buckets. Such that we take mod 4 if anything increases over 5. So the first thing that we do is we figure out that cat will go into this basket right here. So we will put cat right there. Now we look at cop, and there's a collision here. With linear probing, what we do is that we go to the next basket available. So in this case, we would go here. Cop would go in basket number 3. So now we go to ear. Ear goes to 4. 4 is open, so we put it into 4. Now what we do is we look at cart. We can't put it in 2, so we go to the next one. We can't put it in 3. So we have to go to the next one. We can't put it in 4, so we have to go to the next one. Since we're using mod 5, it goes to 0, and we would put cart right here. And that's how linear probing works.